Welcome to the lecture on design of composite trusses. This is the pictorial representation of composite trusses. The behavior of composite trusses is very similar to composite beam. In the composite beam, where rolled sections were used as in the tension zone and the concrete is used in the compression zone. But here in the tension zone, the steel rolled section is replaced by a truss system. So therefore, this structure element is said to be composite trusses. In this composite trusses, you can observe this is a bottom chord member, this is a top chord member, and this is a top concrete. This concrete and the top chord is connected to the shear connector. Under the flexure effect, this shear connector will resist the horizontal shear, and this flexure is converted as an axial force to the top chord member as well as bottom chord member and also the web members. So we'll see uh, the truss configuration. So to go for any composite trusses, you must go for a parallel chord truss. The parallel chord truss in the form of warrant or N type or diamond type or K type. Among this, the warrant truss are found to be more common because the angle is approximately 30 degrees to 45 degrees, where the number of connection gets reduced. So that will be the main advantage of choosing warrant truss for composite trusses or parallel chord trusses. So, in for fabricating those parallel chord trusses, either you can use rolled steel sections or hollow steel sections or built-up sections, depends upon the amount of axial force expected on the member. So this is the sectional view of the composite trusses. The first case is nothing but the top chord is an angle, bottom chord is an angle, web member may be in the form of a rod. And the next case is the top and bottom chords are angle, but web member is also an angle. This is mainly due to the increase in the force in the web members. Then if the top chord member is a little larger in magnitude of axial force it to carry, then in that case you must go for T sections. In addition to T sections, the web members are again an angle section. Sometimes the web member may subjected to medium to low axial forces. In that case, you can go for single angles. If the axial force on the member is also significant, you have to increase the sectional area by providing two angles. So you can arrange it like this. On either side of the web of the T section, you can arrange the angle. So the web member is a double angle sections or double channel sections, depends upon the amount of axial force expected in the web member. To reduce the weight, you can also use a top chord as a hollow sections, and this may be an angle or a channel, depends upon the force expected in the respective members. So in the design of composite trusses, you have to follow certain philosophy or principles. The first one is, as I explained in the composite beam, here again the truss has to be designed in two stages. One is construction stage, another one is composite stage. And in the construction stage, we used to take the self weight of the material, especially the fresh concrete weight, and we'll consider some construction load. Then those loads are expected to taken only by the steel. So since the given structure element is a truss structure, where the top chord is under compression and bottom chord is in tension, because in the top chord, after composite action, it is integral with the concrete slab part. But in the construction stage, the top chord is independent or it is not restrained against concrete. Therefore, this may undergo instability in its behavior and fails due to buckling. Therefore, in the construction stage, we are going to take the top chord as a critical member and will design it that member for the construction stage. The top chord should be safe in the construction stage. Yeah, to make the structure to be stable enough to go for the composite stage. In the composite stage, depends upon the moment or the load acting on the truss, the cross section has to be designed. The last component is stud connectors. Here in this stud connector design, we are going to take the horizontal shear at the interface of the top chord and the top concrete. To calculate the member force in the construction stage, everybody knows that in the construction stage there is no concrete, only steel elements are available. So we have to design as a steel structure in the construction stage. So here this is a top angle. Here in this example I took the top angle is again angle, and web member is also angle. So here I take a particular cross section where top angle, bottom angle and top angle is connected to a shear connector. Here what happens is under the effect of bending, for example, I'll explain. So if this is a beam, this is a beam, see this is a beam. So what happen is it undergo bending. It undergo bending. Say I should say the moment acting on the member is M. So under the bending, this is under compression, top is under compression, bottom is under tension. So you have a resultant force by the top chord as well as bottom chord. The top chord is subjected to an axial force of axial compression of FTA, that is top angle under compression. This is bottom angle under compression. For equilibrium, these two forces are same. Therefore, this equal and opposite force acting at a distance apart will create a moment of resistance. This moment of resistance should be equal to the applied moment for maintaining equilibrium. Therefore, by using this principle, we are going to check the capacity of the top chord member in the construction stage. So taking this as the principle, this is the equilibrium or design equation we should satisfy in the construction stage. This is nothing but design effect, that is the moment actually expected on the beam. How to calculate due to the load? If I know the load, my effect, say MED is nothing but say W L squared by 8. When this will condition comes into effect, when your beam is a simply supported beam. So if we know the load in the construction stage, if I know the span of the truss, then you can able to calculate what is the effect on the truss. So if I know the effect, then for maintaining equilibrium or safe design, your capacity should be always greater than the effect, or for equilibrium this should be equal. So how to calculate moment of resistance? As I explained the earlier slide, the moment of resistance is produced by this axial compression induced in the induced in the top chord and bottom chord member. So another thing you have to please remember, since it is an unsymmetrical section, the axial force should pass through the CG of the section. You know that your angle have an axisymmetry axis like this. So your force is expected to transfer at this particular point. Therefore, I took this force along the CG of the two angles. One is under compression, another is under tension. So if I know that a top angle is critical for my construction stage, therefore I calculate the moment FTAC into the lever arm Z. So I'll take it like this. So if I know the lever arm, if I know what is the target moment to be designed, so here for equilibrium we will make it this two are equal. So I could say instead of MED, I could say what is I equal to MED, where MED will be equal to the force into Z. So here I know what is the moment coming on the stress as well as the lever arm. Therefore, I know what is the expected compression in the construction stage, which is equal to MD, or here MED divided by Z. Now, I know what is the moment acting on the truss in the construction stage. Coming to Z, where this is nothing but, please see here, the lever arm between the force as I told that these forces are acting through the CG of the top angle as well as the CG of the bottom angle. So usually this distance is said to be depth of the truss, because in the earlier or during the analysis, if I want to draw a warrant truss like this, say this is nothing but CG of the element what I have chosen for the top chord. Therefore, this distance is said to be the CG to CG distance of the truss is said to be depth of the truss. Here, therefore, I could say where Z, the lever will be equal to depth of the truss, from which I should know what is the force is expected in the construction stage. For this force, you design the top chord member as a compression member in the construction stage. So rest of the members are not necessary to design it in the construction stage. You have to design it in the composite stage. In composite stage, the concrete hardens and becomes integral part of the steel truss. The steel truss and concrete act as one unit. Then the behavior is said to be composite truss. So under the application of load, the behavior of the truss, say under the load, the truss act as a flexion member. So here under the load, the neutral axis of the composite truss may fall in three possible locations. One is within the depth of the concrete. So here I designate the depth of the concrete is DC, depth of the profile decking sheet as DP, and together the slab depth is said to be DS. So the first possible location is within the depth of the concrete. So then the concrete within the decking sheet not to be considered. Then the next possible location is within the thickness of the angle leg, which is connected to the decking sheet. The third possibility is within the outstand. So we are going to calculate the flexural capacity of composite truss as a whole when the neutral axis is within the concrete or within the thickness of the connected leg, and the and the length of the outstand. So here another important thing, already I have explained that D is nothing but CG of the top angle to CG of the bottom angle, and this is nothing but the CG distance of the top angle from the base of the angle. This is the CG distance of the bottom angle. So here the first case is the neutral axis is within the concrete part, that is this region. So the concrete is under compression and rest of them are in tension. I already we have discussed the same thing in the beam, that this is the tension portion of the concrete. We will always eliminate the tension portion of the concrete for load carrying capacity. Therefore, this is the compression zone and this is the toe zone. Here the tension of the web member will not come into picture, because I'll explain. In the configuration of a truss system, if I am calculating the moment capacity of the trusses, then here the top chord, web member and bottom chord member together act as a truss system. But when you take a cross section at this particular point, where you have only the top chord as well as the bottom chord, web member here, here it is not participating at this particular location. When I am taking another section where I had the contribution of top chord, web member as well as bottom chord member, when comparing the two cases, this is found to be more critical. Therefore, in the stress calculation, we will take the critical case that the web angle is not expected in load transferring mechanism. So therefore, I take the stress block of top chord, top chord as well as bottom chord. This is under compression. So here the lever arm will be of this forces is said to be Z1 and Z2. I'll explain while calculating the moment capacity for this particular case. So here I am calculating the moment capacity of the first case where the nucleus is within the concrete. So here I am applying equilibrium condition. Compressive force will be equal to tensile force. Here the compression here, this is a parabolic, therefore the strength will be 0.36 FCK B effective XPL, because this is the depth of the neutral axis. Then here this is under compression. As I told that web member is not considered for the load transfer mechanism. Therefore here this is the component which contributes tension. So this is the area of the bottom angle and the corresponding says top angle area, and corresponding says this will give tension and this will be compression. When I'm equating the two, I should get, for maintaining equilibrium, we will equate compressive force equal to tensile force. Therefore, you'll get what is the value of XPL, that is the location of neutral axis. If this depth is within this depth of the concrete, then your assumption is correct. This is said to be depth of the concrete DC. Right. So now you calculate, if this condition gets satisfied, then go for the calculation of moment capacity. So in the moment capacity, we have three forces. So you have to take algebraic sum of the forces must be equal to 0, or otherwise you take moment about this particular point. That means you are allowing steel to yield first. This is the axial force in bottom chord. This is the axial force in the top chord. Then I know the force, this is the bottom chord force, therefore I'll take that force into this is the lever arm. The lever arm means, as I explained the earlier slides, the force will act at the CG of this stress block. This is the bottom angle under tension, top angle again it is under tension. See here, this is the CG. From the CG to the CG of the angle is D. Then you know this is the CG. I'll explain here. See here, from this end to this end, this is your Z1. That is calculated by, from this to this distance is capital D, and this distance to the top of the angle is nothing but CXXT, and you add ds. Now you get the distance from this point to the top. Then you minus 0.4 to XPL. You will get what is the lever arm. So that I have calculated for the bottom angle. Similarly, top angle, again you know that here this is the lever arm. So here D will not come. From the CG, this is the C distance, ds minus 0.4 to XU. From this expression, I could get what is the plastic moment of resistance of this composite truss when the neutral axis is within the concrete slab. The next case is when the neutral axis is within the thickness of the top angle leg. So within this leg thickness. So if this is the case, we found that the total concrete is under compression, but we always eliminate the compressive concrete in the decking sheet. In the load, this is to be taken as a reserve strength. Therefore, you take the stress block of concrete alone. Therefore, you're taking only DC concrete capacity, and here some portion of the steel, say here this portion of the steel is under compression. This is under compression. So as we know that to solve this problem, you here what this is actually basically this is not initially available. You add a stress block here, the same stress block is deducted here. Therefore, you will get 2 times Fy by gamma m naught. This is the same principle we discussed in the composite beams also. Now you know this is the whole stress block where you know top angle under tension. Here you have a two stress of, you have a angle leg under compression. Angle portion is under compression. So we will calculate the CG distance because you know this is the compressive strength and over the depth of DC, and here you see this is the area. This area is nothing but I have taken this length of the angle here. This length of the angle is small a. This length of angle is small a. Small a into this depth. How I have calculated this depth? So from this to the top is nothing but XPL. XPL minus DS. I got this distance. So that is the way I calculate the depth of the portion under compression. So into the length I get the area into the respective stress will be equal to the tension in the top chord as well as the bottom chord. This is the equilibrium equation from which you know what is the value of XPL. You know the location of a neutral axis. You check it with the value. If your assumption is correct, then proceed with the moment calculation. So in this moment calculation, you have to take moment of all the forces about the FCC, about this FCC. As I explained, so this two term will be very similar to the first case. Only thing you have a compression. So here these two tensile force will create an anti-clockwise moment, but this force will create a clockwise moment. Here I took this is minus of this is the force I already explained. This is a flow force of compressive steel into the lever arm. Lever arm means this compressive force will act at the center of this force. So from this center, so this distance I already calculated as XPL minus DC. So divided by 2. Half distance plus DC DS minus 0.42 DC. Right. See here, this is DS. I'm sorry, this is DS. This is again DS. DS. I'm extremely sorry. This will not happen. Here you have to do DS. Because XPL will be this much distance minus DS, not DC. Right. So from which you calculate your moment of resistance. Coming to the third category, that is the neutral axis within the outstand leg. Here, what happened? This is completely under compression. This portion is completely under compression, and some of the portion is also under compression. Taking the same thing. Here the area differs. We will take this area separately and this area separately. Now you know this is the stress in concrete, and we are correcting the stress with respect to the top angle. Here you add to have some tension and same to be added. Therefore, the stress and compression becomes 2 times. This is the area in the thickness of the portion, and this is the force due to the area of the outstand above the neutral axis. So with this one, I calculate the neutral axis by equating the compressive force will be equal to tensile force. If I am equating, I got the value of XPL, and taking this XPL, I calculate the moment of resistance as I explained in the earlier case. So if I know the moment of resistance, I can check with the applied moment. If the moment of resistance is greater than the applied moment, then my section is safe to take the applied load during composite stage. After completing the design of top chord as well as bottom chord, so in the composite stage, you know what is the load in the bottom chord under the composite stage. You know what is the force in the bottom chord. So here what to do? You calculate what is the moment in the composite stage, and you calculate what is the what is the size of the top chord member. You can place it and you check it what will be the bottom chord force is expected in the composite stage, from which you check it whether the same section could be adopted for the bottom chord or you have to go for a revised section. Regarding the web members, you are using some analysis principle, estimate the member force, and you design for the member force. Always the member has to be checked for reversal of forces. Sometimes duration, the member may subject to reversal of force. You have to check member against reversal of force. Regarding the shear connector dimension is limited to 2.5 times the thickness of the part to be to the part in which welded, in order to prevent that stud to tear off from the element. This is the guidelines to choose the diameter of the stud connector. Coming to the serviceability check, so here mainly we check against deflection. Since most of the composite trusses are simply supported, therefore deflection will be 5 by 384 WL power 4 ES by I. Here ES is nothing but majority of the material is steel, therefore we'll take Young's modulus of steel. You know what is my W? What W is nothing but elastic weight, that is without any partiality factor you take the actual load. This is the effective span. But coming to the I, you have to take the moment of inertia of the truss. So here you have two stages. One is construction stage, another one is composite stage. I should be calculated for both the stage independently, and you substitute here and you calculate the deflection and check it that this should be less than this limit. So this limit is obtained by from table 6 of IS 800. So the calculation of moment of inertia, I have referred this technical note from which I know that the moment of inertia of a truss is nothing but this is the product of the area of the top angle bottom angle divided by algebraic sum of the two angle into the CG of the two angle, that is the D, CG of the top angle to CG of the bottom angle square. You will get inertia of the composite trusses. So this is for construction stage. In the composite stage, since you have two material, the concrete is replaced or transformed into equivalent steel. Therefore, using appropriate modular ratio, you are converting the concrete to equivalent steel. Therefore, this is to be calculated, and the distance will be here. We have taken the CG of the concrete. Here the top angle CG is not taken because the concrete slab is going to predominantly play in the top portion. Therefore, D plus the top chord CG plus DS minus here, this is said to be that is, this is your concrete top chord and bottom chord. So from the CG of this top chord to bottom chord, you know that this is your D, capital D, and this is your CG distance, CXX. I should say CXX, and this is said to be DS. So here decking sheet, this is the portion of decking sheet. This is your DC. From this center to this CG, I am taking that is where Leverhulme square. So you will get what is the inertia of your composite stress in the composite stage. Using this, you calculate your deflection and check it with your limiting value. Before doing any design, you can use these salient conditions. To design any truss, you have to go for a span to depth ratio, say 15 to 20. Mostly it is suitable for simply supported case. Preferably you can use Warren configuration. And the minimum width of the top chord is to be taken minimum of 120 mm, which is to be found convenient to provide decking sheet during erection. The minimum thickness of the top angle will be taken as 8 mm, which will facilitate good welding of stud with the top angle. The vertical leg will give adequate space to weld the other member or to the gusset plate. And since the top angle is subjected to load in between the member, so it has to be checked against buckling. Sometimes bottom angle also subjected to load in between the nodes, therefore that should also be checked against local buckling. The design limit states for the composite trusses. There are two stages of design. One is construction stage, another one is composite stage. In this construction stage, we have a limit state of collapse and limit state of serviceability. We'll check it only for fracture and serviceability deflection. Coming to the composite stage, you have to check it for fracture as well as horizontal shear, from which you design suitable shear connector, and finally you check with the deflection in the composite stage. If the structure is passed in all the checks, then the structure is said to be safe for the to take the target force. Thank you.